2 years as a research scientist at UT Austin and 3 years with CUNY Advanced Science Research Center in New York as a research assistant professor and founding director of Photonics Core Facility. He joined FIU in 2021 as a tenure track assistant professor. His current research interests are in nanophotonics and quantum optics, with particular emphasis on cross-disciplinary research. And Dr. Krasnok, welcome.
Thank you very much, and thank you for invitation and for coming. So are you gonna record the presentation, right? Okay. And yeah, thank you very much for invitation. And yeah, my name is Aleksandr Krasnok, and I joined recently FIU last year, and I decided to change the narrative of my presentation and to make it more like suitable for our broad audience. And now it's entitled Photonics and Quantum Physics, Recent Breakthroughs and Applications. So yeah, first of all, I would like to advertise my website of my laboratory, and I encourage you to check it out. Here you can find information about the research we are doing and our published works, etc. Yeah, and my today's presentation will be mostly about new types of computing, especially about quantum computing. And when we're talking about quantum computing, first we have to understand why we need quantum computing, right? And there are two main points, like two arguments for developing new types of computing, quantum computing. And the first one is this Moore's law. So the first Moore's law dictates that the number of transistors per single processor doubles every 2 years. So this is exponential growth of number of transistor per single crystal. And this trend was like this until very recently, when the numbers started saturating. So last 15 years or so, we have saturating the number of transistors per crystal, and also other characteristics saturates as well. For example, this operation frequency, sequential processor performance, and others. And even though the total number of transistors still grows exponentially, but this is achieved due to the exponential, the growth in the number of cores in our computers. And there is a second Moore's law, less known one, which says that actually the price and the cost of producing a single processor also grows exponentially as we put more and more transistors there. So at some point, this technology will come to its natural limit, and we need other types of computing. Here I put several numbers. For example, in 1987, the year I born, there was this processor, popular one, Motorola processor, and the characteristic size of the transistor there was 800 nanometers. And even at that time, the processor in the optical microscopy system would look like this. So very complicated structure was many transistors there. And so then in 2004, the year I enrolled to university, the characteristic size was 80 nanometers. The year I defended my PhD, it was already 28 nanometers. Then the year I moved to United States, 2016, it was 16 nanometers. This very popular Intel Core i7 chip. And then in 2018, when I got my first faculty position, it was already 7 nanometers. And very recently, Apple reported this processor with the size of a single transistor of 5 nanometers. And we expect this trend going down to 2 to 3 nanometers about. And this is basically the end of this technology. Why? Because if we pack transistors more and more closely to each other, we have this quantum tunneling effect, a very well-known effect when we have two walls, quantum walls. And if we put them apart a few nanometers, because of this, the Broglie wavelengths of the electron in the silicon, for example, in the silicon, we're working with the silicon, the electron start tunnel from one wall to another wall spontaneously. So you can't control this process. Can't control this process well. So we need new types of transistors, and fortunately there are some. There were some transistors proposed exploiting quantum transport. Unfortunately, those transistors are not scalable. For example, for producing these conventional electronic transistors, we use CMOS technology, which is very extremely scalable. These new types of transistors, they are not scalable, and this is the main drawback of this technology today. Even more importantly, there is a class of conventional electronic computers. They can solve only a part, or like one type of computational problems, so-called polynomial complexity problems. The problems that scale as a polynomial function with the number of constituting elements. But there is another class of computational problems called non-polynomial complexity class, which scale exponentially. No one, even potentially classical computer, can never solve this problem because of this exponential growth of the complexity. So, by the way, please don't hesitate and ask me the question during the talk, if you have any. So we need some class of problems that we cannot solve using classical computers. And apparently the first person who noticed this problem was Richard Feynman, who noticed that we try to simulate quantum problems like dynamics or structure of an atom using classical computers. And he suggested like developing a new type of computing called quantum computer that would be able to solve the quantum problems, finding spectrum of quantum systems, atoms, molecules, their interactions in a new non-classical way. And of course, if this computer would be developed, we would do much more. We could solve much more types of problems, including factorization of large numbers and unstructured data search, very important one. And of course, this first principle calculations of atom spectra, dynamics, new type of chemistry, we would be able to design materials from scratch with some properties at our will using this computer. And one could expect something like designing new types of fuel that producing less carbon dioxide. So even this type of problems like global warming could be solved using quantum computers. So it's very important, I would say, vital, and other problems, of course. So Richard Feynman suggested this idea, and even just after 4 years, David Deutsch was the first person who developed the theory of quantum computing. This was the theoretical paper. And then after 10 years, Peter Shor has suggested a new type of algorithm, so-called quantum algorithm. Now it's called Shor algorithm for factorization of large numbers. And he basically shown that using this quantum algorithm, we can turn the non-polynomial problem of this large number factorization, we can turn it into a polynomial problem and can solve this problem using futuristic quantum computer. And then in a subsequent of works, people first realized the system based on 2-qubit system, and we're gonna discuss what the qubit means here. The qubit is in some sense like a transistor in classical computer. Then this group by Nakamura and Tsai, they have demonstrated that we can use superconducting systems. Now it's called quantum circuits, superconducting quantum circuits, to realize quantum computers. After that, this group from Delft University of Technology, they have reported the first superconducting quantum system of 2 coupled qubits shown here, and they were able to realize this control node gate. We will discuss what does that mean. And finally, in 2019, the group from Google and later from IBM, they have reported quantum supremacy of quantum computers over classical computers. Basically, they have shown that using quantum computers, you can solve a problem much faster than using classical computers. And today, the state of the art is a computer with about 50-60 qubits coupled to each other and controlled using like our classical systems. So to discuss how quantum computer works, let's talk about the general properties of quantum systems, just very basics. So in quantum mechanics, if you have a system like electron, photon, and by the way, when we're talking about quantum, typically people think or assume something very, very small, right? But in fact, even microscopically large, microscopically scale system can be in quantum state. But let's talk about arbitrary quantum system. So the quantum, let's assume that this quantum system can behave in a series of different ways. For example, if this is an electron, it can move along different paths, path 0, 1, 2, 3, etc. So these red arrows, they demonstrate the different options, how the particle, how the quantum system can evolve. And we call these states basis states. And the general property, I mean, the thing of quantum mechanics is that we have to describe the quantum state using so-called psi function or psi state shown here. And this psi vector is represented, psi function is represented as a vector in so-called Hilbert space formed by the basis states 0, 1, etc., all the way up to state n, and n can be infinitely larger. Actually, it can be infinity. So this is multi-dimensional space, and we use this space to represent this the state of quantum system, and and we can find the projections of this vector onto each vector, and we call these projections C sub 0, C sub 1, and these numbers are complex numbers, and and we represent the state as a typical representation of a vector in some space, right? The projection times the basis vector plus second projection, the second base vector, and etc. The second rule of quantum mechanics says that we have to assume that if we don't know exactly in which state the quantum system is, we have to describe the system as it is in all possible states. So in all these states 0, 1, etc., at the same time, simultaneously. But when we measure the state, the quantum system, it gets one of the possible states. For example, it goes to the state 1 or state n, shown here. And the probability of finding this quantum system in the particular state is given by this projection number, C sub 0, C sub 1, etc. Okay, but for applications, we need to select just two possible states, like 0 and 1, because it's much easier to work with the simplest possible system, right? So how we do that? For example, we can put a screen with double slits, and these slits can select the particular pathways 0 and 1. In this case, the representation of the psi function is very simple. It's just two terms over here, right? And each coefficient C sub 0, C sub 1 give you the probability of finding the particle in the particular state. And the Hilbert space becomes two-dimensional, so it's much convenient, very convenient to describe. Yeah, and then if you have another screen behind the first one with double slits, then the interference of these two possibilities create the interference pattern, and so you get some minima and maxima of probability of finding the particle. And if you do this experiment several times, you will, for example, here you will find a lot of particles, the maxima, the many particles here much larger than here. But this is like somewhat surprising result, because this screen creates the shadow actually for the classical particles, right? So interference, we need wavy properties and interference of states, of quantum states. So double slit experiment is not feasible for practical realizations, and we need something more feasible. And to do so, we can use spin. For example, a particle with spin 1/2. Spin 1/2 particles have only two orientations of spin in magnetic field, spin up or spin down. And another approach to use polarization of electromagnetic field, it can be also either up, down, or left, right, or sigma plus or sigma minus, clockwise or counterclockwise polarized. We can also use two-level atom, shown here, and we can actually design. We can even design the so-called artificial atom using these Jefferson junctions, and I'm gonna say a few words about this technology too. So these systems with two possible states, we call this a qubit, two-level system or a qubit, and we use these qubits for developing quantum computers and quantum communications. So let's consider a system of two qubits, first uncoupled, no interactions first, and the total state of this system of uncoupled qubits is represented by a inner product of two psi vectors of each of them. And if you multiply the both, you will get something like this. So this is just the C sub 0 of the first qubit, C sub 0 of the second one, then state of the first one, state of the second one, and etc. The magic happens when we consider the coupling of two qubits together, mutual coupling between them. In this case, we have to describe this system of coupled qubits using the tensor product, which means that we again get something similar to the previous one. So the series of state sub 0, state 0, 0, 0, 1, etc. But the critical point here, very important one, is that these coefficients C sub 0, 0 now cannot be represented as the product of two, of C sub 0, C sub 0. And for others, right, for C sub 0, 1, etc. So the state becomes unseparable, not separable. You cannot represent the state as a particular, as a state, as a product of two states of two uncoupled qubits. And we call this, yes, Jason, go ahead.
Hey, Alex, I'm sorry to interrupt. I just have a very quick question. You mentioned that the C0, C1s are complex members. Yes. Is that right? So what is the intuition behind all these complex numbers? What does the number represent? I guess can you just
yeah.
I can understand linear algebra, but when you get to the complex numbers, that stretch my math.
So yeah, sometimes you can hear that no one really understands quantum physics, and this is really, I mean, the case, because we described the quantum system using this psi vector, which is not physical, because this is not a real wave. This is just a mathematical approach to describe the system, quantum system, because we cannot suggest a classical interpretation, right? This is why the wave particle duality and other points. And in order to combine the both wave nature and particle nature of the quantum system, we have to take into account the interference and wave properties, basically. So this complex valued coefficients C sub 0, C sub 1, they contain the both phase and amplitude. In order to get the interference, you need phase. If they if the phase is coincide, you get constructive interference. If they in quadrature, you get destructive interference.
So
because of the wave.
Right.
Because
so
of
this
the wave
is
nature.
like the signal processing aspect of those complex numbers, or sort of like a match to those representations.
Yes. Yeah. So yeah, I guess yes. Yeah, exactly. So for the system of two coupled qubits, we cannot represent the coefficients as a product of two, and we call this quantum entanglement. When the state of the first qubit affects the state of the second one, right? And also now, instead of two coefficients to describe the system of two qubits, we need four coefficients: C sub 0, 0, C 0, 1, 1, 0, 1, 1. And if we couple three qubits together, we would have already 8 coefficients, which are not separable, 8 coefficients. And in general, if you have n system of n qubits, you would have 2 to the power of n coefficients to describe your system of n qubits. For example, 2 to the power of 20 is this, like about million. And 2 to the power of 50, this is like state of the art today. There are a number of quantum computers realized with 50 controlled qubits. We get this large number. And this number is already something that cannot be processed using classical computers. This is kind of a milestone here. So, and this is called quantum parallelism, which means that we combine a system of several qubits, couple them, and we can encode a lot of information into this system. 50 qubits, for example, atoms, is virtually nothing, right? 50 atoms, very, very small. But we can encode a huge amount of information there in the system. Quantum parallelism. So how a generic quantum system looks like? So first we have some input qubits that we can set to a particular state using some external stimuli, pulses, etc. Then we have the quantum logic circuit, and we can program this circuit according to the quantum algorithm. And then this logic does some information, the quantum information processing, and the result returns to output qubits. In contrast to the generic Turing machine, right? This system doesn't have memory. Why? Because all the possibilities, all the couplings, all the possible states in the system proceed simultaneously. And then we measure these output qubits and get the result. And if needed, we can run this cycle several times and collect the statistics in the output. In order to realize the general quantum computer, fortunately, we need only 3 single qubit gates and 1 qubit gate. The 3 qubit gates, the most important ones, I guess, like we typically use, are X gate, Z gate, and Hadamard gate. So without going too much into details, how we realize these gates? In few words, we have a system like two-level system, like shown here, and then we can control the state of this two-level system using external pulses, like electromagnetic field, and choosing the right duration of this pulse allows us to change the state of this qubit to a new state. And yeah, varying this duration, we can change this quantum state, and this is how the single qubit gates work. For the 2 qubit gate, the most important one is this C0 gate, and it gets control qubit and target qubit. So this is a system of 2 coupled qubits, and this is how it's denoted in the electrical circuits, in the quantum circuits. And the truth table is shown here. So if we set control qubit to the state 0, it returns the same target state from input to the output, right? It doesn't change the target. But if we set the control gate to the state 1, it flips the target qubit from 0 to 1 and from 1 to 0. The very important point here is that we never have either 0 or 1. We always have the superposition of both. And this quantum gate does all these possibilities simultaneously because of this quantum parallelism. And again, without going too much to the theory, the 2 qubit gate is the system of 2 coupled qubits controlled by 2 pulses with different duration and slightly different frequency. For example, so let's suppose we have quantum circuits like this, and this is called golden 2 qubit gate. We have first so this is the input qubits. These 2 are output qubits. First we have the Hadamard gate, and then this C0 gate. So if we set the input qubits to the state 0, 0, after Hadamard gate creates the superposition of 2 states. Like from 0 state, it creates state 0 plus state 1. And in result, before this C0 gate, at this point, the quantum state becomes like this. This is a superposition of states 0, 0 plus 1, 0. So this state is trivial because we can represent it as a product of 2, as a product of state 0 times state 0 plus state 1. Trivial state. But then after the C0 gate flips the second qubit here, the state of the second qubit from 0 to 1, because the first one, the control qubit gets state 1. So now it becomes the new state 0, 0 plus 1, 1. And this is very important because mathematically, this is just a flip of one number here, right? This 0 to 1. But in contrast to this state, which is separable, we get unseparable state. It's called Bell state. And this is the state with the largest quantum entanglement. we cannot represent this state as the product of two psi vectors of two separate qubits. And these Bell states are very important for quantum teleportation, for quantum computing, and so and etc. For example, if we have two person, we call this person Alice and Bob, and assume that they created this Bell state using this golden circuit, and then they put apart these two qubits. They basically share these two qubits, and the Alice and Bob, they can be far away, like Alice on the Earth, and Bob on the Moon, for example, very far away. The rules on quantum mechanics dictates that the Alice and Bob, they still have this entangled quantum state that has been created at some point. And then let's suppose Alice measures her qubit, measures the state of her qubit, and she can obtain either state 0 or state 1 as a result of this measurement. And after this measurement, the Bell state is collapsed to the state 0 or state 1. And now, if Bob does the same measurement, he finds his qubit in the state 0 or 1 with 100% certainty. This is a concept called shared randomness. So, in other words, the result of measurement at the Alice state, at the Alice part, affects the state of the Bob's qubit, and this quantum entanglement destroyed after this measurement. So they again have to create this coupled system or coupled qubits, then split them, share them, and then they can do the same. So about quantum computer simulators, today we have a number of software to write quantum algorithms, and here I present several, most like widespread, including these QS simulators, Cirq, Qiskit, Forest, and QDK. But I particularly like this Qiskit quantum simulator, developed by IBM company. They have a very good website, very good tutorial, and so on. And they also allow people to write the code and run the code on one of their real quantum computers. So you can remotely run your quantum algorithm on using one of those quantum computers, which is very nice. Yeah, so I encourage you to go to check their website. This is very nice introductions, particularly for students, etc. So if you so far, if you don't understand how the quantum computer works, I wanna illustrate this idea using this problem of maze. So let's suppose you have a complicated maze, like shown here, and you have input to the maze, and probably you have output, and you need to find the way out from input to output. So the classical computer would do the blind search. Classical computer will try all these possibilities one by one, and this process, this blind search, will take forever for a very complex maze. But instead, for example, if you ever find yourself lost in a cave, like shown here, you wouldn't try all possible ways there, right? It's not practical. What you do instead, you would give a cry. And what does that mean? It means that you send the acoustical wave into all directions simultaneously. And then if there is a person at the output, the person will hear you out and will come and save you. So this is like a nice illustration how the quantum computer works, basically. So here I put a simulation of a quantum particle source and a maze, and we send this wave inside the maze, and the wave propagates to all possible directions simultaneously, and then eventually finds the output. And to do so, we need wavy properties of the particles, which is described by our psi function or psi vector, and interference. That's why we have to assume these coefficients C sub 0, C sub 1, etc., complex valued. And then the constructive interference of the waves will give you the correct wave from input to output. So, as I said, there are some quantum computers already exist, and the progress in this area is really fascinating. And so this table represents the state of the art in this area. Different realized quantum computers. So the largest number I was able to find contains 127 qubits. And you can also see that the vast majority of the quantum computers, they realized using these superconducting systems. And with two exceptions, photonics, recently proposed photonic quantum computer, and based on trapped ions. So speaking about superconducting quantum computers, so how it works in hardware. So to realize quantum computer, we need a resonator, or quantum resonator. But what a quantum resonator looks like? Actually, if you have any type of resonator, like shown here as a coupled LC circuit, very simple one, right? It gets a resonance, and without excitation, it contains a lot of photons from thermal noise. Because of the finite temperature, there are some thermal noise photons, and this resonator is always populated with a lot of photons, hundreds, thousands. At room temperature, it can be a very large number. So we cannot use this resonator to realize quantum computer. What we do, we cool down the system down to the critical temperature of the superconducting state. When the circuit becomes superconducting. Superconducting means no dissipation. The state there can live for a very long time, theoretically forever. But unfortunately, even at this temperature of 10 Kelvin, the resonator still contains a number of thermal photons, noisy photons. So we need to cool down the system even more down. Practically, this temperature must be below 100 millikelvin. The lower, the better. Like 20 millikelvin, this is the temperature of people use in the lab. And of course, this is very difficult and so on, but people solve this problem. And below 100 millikelvin, you empty up your resonator, and in like mean number of photons in your resonator became less than 1. So it's virtually empty resonator. But even in this case, we cannot use this resonator for quantum because the energy levels are equidistant in this system, equidistant. So if I put one photon, then another photon, my energy of this system will jump or be promoted to a higher and higher state. So this system doesn't work as a qubit. We need qubit. Qubit means two possible states. So we need some sort of nonlinearity to make this system useful for quantum. And yeah, and in order to introduce the nonlinearity, we put a device which is called Josephson junction. And this is a lossless, very nonlinear system that allows to select just two states, the ground state and first excited state, and use these states as a quantum qubit. And this is a particular like circuit for one qubit, as it looks like on a chip. And this technology is very scalable. We can fabricate hundreds, thousands of these qubits on a single chip. That's not a problem here. Very scalable approach. So speaking about challenges in this area. So the first challenge is the time of quantum coherence. Basically, the time when we can use this quantum state for computations, for quantum computations. This time is relatively short. In the state of the art here is like 1,000 milliseconds. So, but yeah, practically it's much less, like 100 milliseconds or even tens of milliseconds. This is the typical number we have in the lab. We can make this qubits to live longer, putting them to the very good resonators, but unfortunately this approach make them very slow, like excitation of them very slow. So like we're still working in this direction, and this is like very important research direction today, how to make a better, more reliable quantum circuit, quantum qubit. And in my lab, we are working on this as well. The next challenge is illustrated by this figure, by this picture. This is a computer of like 10 qubits, but even for 10 qubits, we get a bunch of cables, microwave cables and microwave facility here. And for 10, and this microwave facility again scales exponentially with the number of qubits. And if we have 100 qubits, if we would have 100 qubits, we would get a lot of these wires, a full room of cables. And but we need something like 200s or 500s or even 1,000 qubits. And today we don't have like an idea how to arrange the controlling and setting and I mean basically how to arrange all this microwave facility to work with that quantum computer. Another challenge is represented by this schematic of quantum computer. So here we see the quantum circuit cooled down up to 20 millikelvin. This quantum computer can be excited through excitation channel over here and controlled over controlled channels shown here. But then in order to prevent room temperature noise going through these channels, we put a set of attenuators here, here, and here to attenuate down the signal and the noise as well. But unfortunately, for the outgoing channel, for this information channel, we cannot do the same approach because we need as much signal as possible. And due to the reciprocity principle, high transmission from in one direction means that we must have high transmission in the opposite direction. So a lot of room temperature noise will go from room temperature apparatus down to the quantum computer and destroy it. And that's why we need using these circulators and isolators to prevent decoupling room temperature noise to the quantum computer. Unfortunately, these systems, currently available systems, they use magnetic fields, and magnetic fields bring another type of noise. And also these systems are lossy, and magnetic field is harmful for superconducting states. You know that at high magnetic field, the superconducting state becomes like usual conducting dissipating state. So we need to get rid of magnetic materials from this system. And in my lab, we are working on this, exploring two different approaches. First, using nonlinearity, intrinsic nonlinearity in the quantum systems, so-called quantum nonlinearity. And in our recent work, we have shown the system having very high isolation for a very simple system of 2 qubits. And in fact, now we are working on realization of this idea with our friends from Australia. And another approach we are interested in and actively working is using novel materials, for example, topologically non-trivial materials like Weyl semimetals. These Weyl semimetals, they have no total magnetization, but at the same time support non-reciprocal behavior. And in our recent paper, we have shown that we can use these materials to realize a good, reliable optical isolators suitable for quantum computers. So my last point, how much time I have left? Just a couple of minutes, right? So we started a little bit later, so maybe I have another 10 minutes or so. So speaking about computers, imagine something like this on the right side, right? A computer that, like desktop, we use for different purposes, rather than this quantum computer. And one can ask a question: would this quantum computer be personal ever? And of course not, because this is very complicated, sophisticated, expensive system for very specific type of problems, for some non-polynomial class of problems. But at the same time, we think that we can develop so-called optical computer, so-called photonic computer, to work with optical information directly without changing it from electronic to photonic ones. This work is motivated by the fact that about 80% of current information globally is transferred over, using these optical fibers. So we use these optical fibers for internet and other types of communications. And this map illustrates the intercontinental optical fibers, cables that connect different data centers. But when this information encoded in light comes to the data center, it transfers again from photonics to electronics. And this process is very inefficient in terms of loss and speedness, etc. And in fact, one typical data center consumes energy sufficient to power a town, for example, according to this recent DOE report. So we need to develop optical computer that would be able to proceed optical information without transferring it to the electronic information, right? And the crucial, like the most important point here is that photons actually are very large particles. The typical size of a photon is given by wavelengths, which is about 500 nanometers. Comparing to the size of the electron, it is about 100 or 1000 times larger than the size of electron. Meaning that if we simply scale electronic system to photonic system, the photonic system will be much larger, which is not feasible at all. So we need to somehow squeeze the size of the photon down to nanometer scale. To do so, we use this device called nano antenna. And in my lab, we also designed these nano antennas to be able to squeeze light down to nanometer scale. And then we can use this scale, like squeezed light, for different purposes. For sensing, for non-classical quantum states, probably for optical computers, etc., etc. So nano antennas. Another point why we need photonics is illustrated by this slide, which represents different kinds of recently proposed quantum materials, starting from graphene, two-dimensional transitional metal dihydrogenides, perovskites, NV centers, etc., etc. All these materials, we call these quantum materials, they were reported recently, and now we use them to develop very different systems, starting from quantum sensors, chips, and so on and so forth, for different purposes. And this slide illustrates some of our recent works. Some of them were chosen for the cover image in these journals, and I encourage you to check out my website to see the full list of our works, and publications. And to conclude, I just want to show the current progress in photonics. And this first example illustrates the hybrid optical computer, where we use photonics to boost up electronics. Another work is artificial intelligence. Apparently, photonics became very efficient and very useful for artificial intelligence because we can use these optical systems on a chip for this purpose. LiDARs is another technology that we use for navigating electric vehicles, etc. And quantum computers. Yeah, as I said, these recently proposed photonic quantum computers based on optical systems are very useful, and they have several benefits over superconducting systems, because optical quantum computers work at room temperature and exploit conventional optical elements. And for example, this Hadamard gate, very important one, in optics, this is just a beam splitter. In fact, you put beam splitter and you get this Hadamard gate, and that's it. So several points to take home. Quantum computers are absolutely essential for some types of mathematical problems. The current progress in the field of quantum technologies, although outstanding, is only the beginning, and we need a new generation of engineers with the deep knowledge and training in electrical engineering, optics, quantum materials, and quantum technologies. And at this point, I would like to advertise my recently established course on quantum technologies and quantum materials. I teach this course this and next semester at electrical engineering department. So if you are interested, please join our group. So next, optical and hybrid computers will be the next generation of personal computers. The peculiarities of photons, their size and lack of self-interaction, make us to explore new materials and their optical properties. And this is something we also do in my lab. Next, optical technologies and their combination with quantum technologies open a number of important applications and applications that are changing the world right now, in fact. And yes, that's it. Thank you very much for your attention, and the talk is open for your questions. Thank you.
Yeah, thank you for a wonderful talk. And now we would like to see questions from our audience. Anyone have a question?